Hello everybody, my name is Gabe, and today I'd like to talk to you about graceful labelings for graphs. So let's start out by giving a brief description and example of graceful labelings. A graceful labeling is a labeling of a graph with m edges such that each vertex is labeled with a unique number from 0 to m, and the edges are labeled with the absolute difference between the corresponding vertex values. And also an edge ranges between 1 to m. So in this case, we see that the vertices are labeled from 0 to 8, and 8 corresponds to the number of edges in this graph. So in this case, m is equal to 8. And we can see that the edges between those vertices are labeled with the absolute difference between them. So from 0 to 8 is going to be a labeling of 8. From 1 to 8 is labeled as 7, and so on. And each vertex is uniquely labeled in the set of vertices, and each edge is labeled uniquely in the set of edges. But note that not every value in the ranges from 1 to m or 0 to m need to be present. The labelings just need to uphold said properties. So in this example we'll see in a second, we'll show this. So in this cycle graph right here, we see that there's 4 edges, and the vertices are labeled from 0 to 4, which upholds one of the properties of graceful labelings. But as we can see, there is not a vertex with label 1, yet this is still considered a graceful labeling, so that just goes back on a note that I just talked about. So just keep that in mind whenever you're looking at a labeling for a graph. Before we move on, I'd like to talk about some additional facts. So let's start out by saying that not every graph can have a graceful labeling. And in graph theory, people like to call those ungraceful labelings or ungraceful graphs. And on connected graphs, there are m factorial labelings on a graph with m edges. So that's m factorial different labelings. And also there exists a near graceful labeling, which is very similar to graceful labeling, but not quite. And one of the properties is that each vertex is uniquely labeled with integers from 0 to m plus 1. So in graceful labelings, it's 0 to m, but this one's m plus 1. And edges are uniquely labeled with integers from 0 to m plus 1 and not 1 to m. So basically a difference of 1 for the ranges, and that makes it a near graceful labeling. Before we go on to proofs and algorithms, I'd like to talk about 2 of the more popular / notable conjectures. The first one being that all trees are graceful, and this comes from the graceful tree conjecture / the Ringel-Kotzig conjecture. And we can see in the small example that I put right here that this is a graceful labeling for a tree. And it's pretty easy to prove, or at least find an algorithm for smaller sized trees. But since nothing can be really proven to be true until you know something upholds for size infinity, that's a pretty large feat to prove for trees of size infinity. So this is a conjecture and not a fact. Also, another conjecture I'd like to talk about is Rose's conjecture, and that's that all triangular cactus graphs are graceful. Now, within the lecture, we haven't talked much about cactus graphs, so I'll give a brief description. And those are connected graphs in which any 2 graph cycles have no edge in common. So we can see in this small cactus graph that there are 2 cycles, but they do not share an edge. And here is a proof / slight algorithm that I found, and I also drew my own example to help explain this proof / algorithm. So let's say that this graph starts out as being unlabeled. So we'd start at the root right here. For this example, I just started at the top. And we'll label that 0. And what we'll do for the first set of our vertices is we will skip 1 and add 1 plus the value of the vertice that we just visited. we will repeat that until we can't skip to another vertice or vertex. And those will be our vertices in our first set. And then before we go on to the second stage, let's assign a value to a variable called q, and that's going to be the number of vertices minus 1. So in this case, our vertices, there are 6 of them, so q is going to be 5. And for our second set, or second little step to label these vertices, we're going to start with q in the second vertex, and we're going to label that with the value of q, and we're basically going to do the opposite of what we just did, and we're going to subtract 1 from the value of the previous one. And by the end of our little algorithm, we're going to have one set, which is labeled from 0 to q divided by 2, if q is even. In this case, that's not. So in this case, this first set is going to range from 0 to q divided by 2. And so we're going to round down after division. So 5 divided by 2 is 2.5, but we're going to round down to 2. And so we can see in our first set, the vertices are 0, 1, and 2, so that upholds. In the second set, we'll label its vertices with numbers from q plus 2 divided by 2 to q if q is even, and q plus 3 divided by 2 minus 1 to q if q is odd. So in our picture, it's not quite as sequential as I'd like it to be to explain this, but in terms of organizing our set, we're going to have it go from least to greatest. And so starting out, since q is odd, it's going to be q plus 3 divided by 2 minus 1. So it's going to be 5 plus 3, which is 8, divided by 2, which is 4, minus 1, which is 3. And that goes all the way up to q, which is 5. So if these properties uphold, then you have yourself a graceful labeling, and this can be used to prove that every path graph is graceful. Now this is a much more complicated algorithm, and I encourage you to go look at it for yourself. I found this from a research paper on graph theory and graceful labelings, and this is very hard to decipher even when I was doing my research. So I basically tried to summarize what this algorithm is attempting to do within just a few bullet points. So we're going to start with an unlabeled graph, and f, which is the function of r, which is going to be the root value, is going to be equal to 0. So that's kind of reflective of what we just did with this algorithm, is we started at this root, and the value of that root is equal to 0. And basically, each iteration of this recursive algorithm is going to attempt to create a new edge with label k by labeling an unlabeled vertex u adjacent to an already labeled vertex v, such that the absolute difference between them is equal to k. So let's say if we didn't have this 5 in this vertex labeled with 5, and we wouldn't have this k value, obviously. So 0 in this case would be our already labeled vertex v. So u would be this unlabeled vertex. And we basically assigned this a value which hasn't been found within a labeled vertex. We'll assign that, and k will be the absolute difference between those. And that algorithm will basically go through the graph and check that the values of a graceful labeling are upheld. Once again, this algorithm is pretty complicated, so I'd encourage you to go do your own research on it. But this is basically what it's attempting to do. And also, when I was doing my research, I found a lot of great resources that you can go and look into. I especially found the resource with this research paper pretty interesting. It's pretty technical, but you'll learn a lot about graceful labelings and like the more scientific, logical approach to finding them and explaining them. And also this mathworldwolfram.com article on cactus graphs is pretty cool because I'd never even heard of a cactus graph. But I definitely encourage you guys to go and do some more research on it. But that'll be all for me today, so I'll see you later.